welcome to calculus, physical science in the AM. We had a false start before. Okay, we're taking up these sheets. I'm repeating myself because we're recording. And these problems were already worked through. You can pause the video if you need to get done. Okay, so where I was is that we were on the second page. Theoretical yield is just the same problem we had been doing last week, stuff like this, but we need to use the limiting reactant. And I mentioned that. Normally we start the limiting reactant, C78603 we determine. Normally you'd start with the grams and convert to moles, and you could do that in here, but the work is done, so I'm going to write down this as my starting point for the next. You could start with the grams, but it's just work is done. So I'm going to remember what we're talking about. 0.0999. Okay. And that is the C78602. Your normal first step is to convert to moles if you need to. It was already done. So now we have to change count. And that is C7H6. There's no math involved with this because it's 1 to 1. Aspirin. I don't expect you to know what aspirin is. I'm going to put that and we'll double check this. It says here, form aspirin. John H. That's the chemical we want. Now, if I stop calculating, I have moles of aspirin at this minute. But theoretical yield means how many grams. So that means I have to do some adding. Let's calculate. So 9 carbons times 12.01 plus 8 times 1.01 for hydrogen plus 4 times 16 for the oxygen. I get 180.17. You guys are double checking everything I do. I don't have an answer to questions I made up. So far, I'm okay. If I just see anything on the top, I multiply it, and there's no division. Times 0.099. I get 17.998983, but I only need 3 significant digits. That's 18.0. I'm going to put down the chemical. That's, in theory, everything that went 100%, how much you should get. But the next question is asking for a percent. When the experiment is done, you didn't get 8, only 16 grams. So the percent yield is equal to the 16.6 grams you got out of the possible 18 times 100. 16.6 divided by 8. 92%. 92%. Okay. Any questions on this last bit? This one. Silicon dioxide. That's the SiO2. 15 grams of that's reacted with 12 grams of graphite. In case you didn't know, graphite is bracket C. So that's coming. Graphite. Where do you use that, by the way? Maybe your pencil, right? So pure carbon can be in the form of graphite, and if it's under pressure and heat, in the right conditions, it forms diamonds too. There's a big difference. Okay. Calculate the moles of silicon dioxide in grams, as we do start with moles. So 15 15 grams. SiO2. Silicon dioxide, 28.09 plus 3. Is that 50.09? 60.0. Yeah, I caught myself as I was saying. 60.09. So 15 divided by 60. What do we get for a 3 decimal answer? Properly. Other people in agree? Agree? Then we're going to calculate the moles of the graphic. Yep. 2 quarter. Yeah, 15 out of 60 is a quarter. 2. Nobody's in agreement. 0.249. This is what I'm asking. No. I'll just start. 0.249. Now let's go. Okay, 0.2496. The 3 digits. See, I should have just typed this in. So, I knew it was around a quarter once you corrected me. Yeah. 2496 is 257. 3 digits. Okay. Significant digits, we'll wait till next. Good morning. Welcome to Physical Science in the AM. In case you just joined us, the class is in progress. This is Physical Science in the AM. Come on in, have a seat. Anyways, 12.4 grams of calorie. I'll take this one in. I trust no one now. I know it's around 1. 12.14. 12.01. I have developed trust issues from a long time ago. When I was a kid, I think the first time I had trust issues, and I realized, gosh, thank you. There's a game I used to love, Donkey Kong, and I play all the levels. There's never a donkey in it. I always thought it was the donkey I thought was going to come out. No, it kept being that big gorilla. Anyways. How is the gorilla a donkey? King Kong, yes. Donkey Kong. Anyways. Okay, the balanced reaction is given. Identify the limiting reactants. You just choose one of these. Which one do you want to choose? I usually choose the first one. Carbon? Sure. So, if all of the carbon react, this is what I'm thinking. So I go 1.03 moles of carbon. You may have done the first thing. How much, well, according to the balanced reaction, 3 carbon. How much silicon dioxide? When I divide that by 3, I know it's 33-ish. 1.03. Divided by 3. 0.343. So if all of the carbon reacts, all of the graphite reacts, 0.343 moles of silicon dioxide are needed. Do we have that much? It will run out. The silicon dioxide will run out before we get there. Here's my thought process that I'm writing down. 0.250 moles SiO2. That is from I'm going to say, what's the limiting? Therefore, with 3 dots, right? FiO2. It runs out before the other one. You're going to come to the same conclusion if we started with the same conclusion. You have more than enough carbon. So incidentally, I'm going to just write down the graphite. X. That wasn't necessary, but this is the kind of things you're thinking. Okay. Now, I kind of explicitly write it out the thought. Questions here? I know some people are drawing. Welcome back. This is Physical Science in the AM. In case you've just joined us, I'm your host, Joel Schdelka. Hot dog, we're continuing on. Okay. Excess reagent. We already said what the excess is. How many grams of the excess reagent remain? Well, to answer this part here, and remember, reagent is just another word for reactant. How many grams of that excess reagent remain? I'm going to flip that because we've got to think about this a little bit. Flip back too much. Okay. So, we have 1.03 moles of carbon. That's what's in it. We know that not all of that's going to be used, right? So if we use the limiting reactant, we'll figure out how much carbon is actually used first, okay? So this is what we're going to do. We're going to go with the limiting, that 2,5. Just thinking this to myself. 0.25 moles, I'm just trying to remember this. So we start with our limit. 0.250 moles of SiO2. We want to figure out SiO2 change to carbon. We look up again, and I'll be flipping. Long. Okay, so this helps because I have no measure. The carbon ratio is 3 to 1 with the silicon dioxide. At this point, if I start calculating, we'd have the moles of carbon that are actually used. We want to find the grams. That won't quite fully answer the question, but that's the next one. Carbon is equal to 12.01 directly off the periodic. Okay, 12.01 grams. I'm going to calculate, right? 0.25 times 3 times 12.0. 9.0075. I'm going to call it 9.01 grams of carbon. Used. Still trying to find the excess. So I'm going to remove this message here. Remove this one. Do that again. Right. There we go. Once I've done that, to figure out the excess, I'll flip back another second. See, how much did we start with again, gram-wise? We started with 15 grams of silicon dioxide. The logic is just subtract. So, grams of excess remain. 15.0 grams carbon starting minus what we used. That's 5.99. Okay? My mental math is pretty mental. That means 5.99 grams of carbon is the excess. It's not left over. Okay. That makes sense? Pause for a second.
Can you multiply by 12 and then do 3 over 1 less?
Multiply which by
So for your first equation, you go 12 over 1 more and then 3 over 1 in the next bracket?
Oh, for part D, you mean?
C.
Oh, for C, the one we did.
Yeah.
I'm going to write down, I'm not sure I understand exactly. So 12 what? 12.
No, could you go 0.25
Okay.
times 12 and then 3 over 1?
Oh, 12 because of the grams per mole?
Yeah.
12 over 1? Yes, mathematically that's the same.
Okay.
Yes, as far as calculator entry, I sometimes do it differently. The reason why I write this in this order all the time, though, is because you see the logic. I first get rid of the chemical, I have moles of carbon, then I convert the carbon to grams.
Okay.
Mathematically, it makes no difference, but logically, it just doesn't make sense when you think left to right as well. If it makes sense to you, though, and you're consistently getting things right, keep it. Now, what's the theoretical yield? So we can start with the limiting reactant, limiting reagent. It's already in moles. And we're going to change, get rid of this silicon dioxide. This is the reason why I do this. And we want moles of silicon carbon, SiC. Yeah, it's also a 1. So mathematically, it doesn't matter. But it's necessary because we need silicon carbon. Yield, we want in grams. Silicon, 2809 plus 12.01. Going to be 40.10. Correct? Okay. So a quarter of 40, we know is 10, but I'm going to just type it in because I'm not sure of the decimal. Oh, actually, they're not sure. 0.25 times 40. 10.025. So 10.0. But we don't want 10.02. We'll just call it 10.0. Read it. So in theory, you should get 10 grams. That's the yield. Anyway, the theoretical yield should not be. Yes, it is. Thank you. Old man is slipping. Keep this up. Thank you. How many grams of silicon carbide are produced if the percent yield of the reaction is 95.4%. It's kind of backwards. Just so we can think about this, I'm going to put down the formula for percent yield. Is equal to, I'll call it the actual yield by the theoretical. Okay? That's the formula you can use. You didn't have to write this out, but I just wanted to say where we're coming from. There's more than one way to think this one through. Here's a one. I'm replacing percent yield with 95.4%. The actual yield is what we're trying to find. So I'll just call it actual. The theoretical yield we figured out is 10. And then times 100 is part of the times 100% is part of the formula. Now, I'll do 2 or 3 steps. So I was going to just jump to the answer. But if we divide both sides by 100, just to do it in another color, that part I can do. 0.95. Okay. Then I cross multiply. I want to get actual yield all by itself. So I multiply 10 by itself. 0.954, which is 9.54. 9.54. That's grams of silicon carbide. All right. So that one was a little variation. Now, like I said, you understand percentages. I could have just jumped into 0.95 times 9.4 times. I don't care as long as you're consistent. A lot of you are pretty mental. What I'm going to do